Bob's from analog electronics up to software design, but his passion is low-level code. His talk will help you comfortably do more with less and supercharge your projects by applying basic knowledge of assembly. Please welcome to the Hackaday Supercon stage, Charles Lohr.
Hello. Oh man, it feels so crazy to be on the main stage, and I wanted to thank everybody at Hackaday. Like, so many of us creators would not be noticed, would not be seen if it wasn't for Hackaday, and Hackaday is the people who made most of my life, my adult life, like what it is. So I really appreciate everybody at Hackaday. This talk is going to go super fast, so don't worry if you don't understand something, if you skip over something, if you can't follow, that's fine. I'm mostly here to give you a bunch of things for you to be able to Google. So a little bit about me. I am Charles Lohr. I have a YouTube channel, and I haven't really been uploading that much recently. But instead, what I have been doing is been working diligently on GitHub. So a lot of times, if you're working with an expressive part or something like that, and you're Googling how to do something unusual, hopefully you're coming on some of my work. So just as always, science is still my verb, Christ is my light, but I'm just not really as much YouTube-y and much more just producing GitHub stuff now. So the whole point of this talk is that you spend many hours with the computer, and that's a little bit like being in a relationship with your computer. But you don't normally speak the same language as the computer, so sometimes there can be misunderstandings, and that'll leave you a little bit like this Pikachu here. So through the talk, I'm going to give some stories, kind of an introduction to assembly. I'm going to give some examples, and I'm going to give the tools, this is the big part, is the tools, on how you can learn more about assembly yourselves. And I have a couple more stories after that. So the first really interesting story, I don't know, who here has played Rollercoaster Tycoon or is at least aware of it? Okay, okay. Who here knew that it was 99% written in pure assembly? Okay, so it's not everyone, okay. So Chris Sawyer decided, I want to go write this game 100% in assembly. He negotiated a really good rate, like percentage of the ownership. He personally got $30 million for writing this game, which can support thousands of patrons. It totally blew everybody's minds at the time of what could be done when computers are used really efficiently. But that's not really the direction that I want to head with this as much. What I'm much more interested in is sort of how is assembly used in more practical ways. So for instance, Doom, and a lot of people here, you probably are aware what a tour de force of engineering Doom was, but out of over 60,000 lines of code, there's only about 190 lines of assembly. And that's because John Carmack was very responsible and knew exactly just how to salt with the assembly, which is what I would encourage all of you guys to do. Don't go buck wild with it, but find the places where it makes sense to learn about it and potentially use it. So we're going to break it down. There's lots of different approaches. We're probably not going to use that much assembly, but we might not. That's okay. And we're going to be able to think more like the computer and more like instructions. There's two major things that I want to hop on before this, or I guess three before we really dig into assembly. One is Amdahl's law. So this is the principle that if you optimize something for time, for speed, for space, if you optimize it, it only impacts the part that you optimize. So if you spend all of your time trying to hyper-optimize something, it only takes 5% of the computer's time. That's probably a waste of your time. So focus on the things where it's spent. So the idea is you want to avoid any kind of premature optimization. You want to avoid making trade-offs with readability. Like if you go and hyper-optimize this really important piece and now nobody else can read it, that's a problem. And the idea is you always want to test to make sure that what you think is going on here is really what is happening. So what you'll have is you'll have an original process, and so some engineers, a lot of us, want to go really focus on this one piece that I know how to make fast, and I'm going to make it 5 times faster. But actually, if you just spent like 10 minutes and made A faster, you would have been a lot better for the end user. So some of the other things that you might want to consider doing first is just reorganizing your loops. If you have an if statement or other fors or things inside your loops, just bump them outside, and there are huge benefits to be gained there. If you're doing things where you're just searching through a list, one element at a time, when you could just use a dictionary, might want to consider those kinds of things first. Assembly is kind of one of the last points where when you really need to make something better. The next one is, we're going to talk about C a fair bit here. If you use other languages, that's totally cool too. I like C because it automatically kind of makes you think a little bit more like the computer. So for instance, like this is just an interesting point. This is comparing the performance of C programs compiled natively for the computer versus if you cross-compile to JavaScript. A lot of people here probably have the impression that JavaScript is slow, but the answer is it's only slow when you write it to be slow. So there was a project where they cross-compiled C programs for different things like Physics Engine and Lua, like performance benchmarks, and they compiled them from C into ASM.js, which is a subset of JavaScript. And if you look, it's really not that much slower. It really has more to do with how you're telling the computer what to do and what you're telling it to do than your choice of language or anything like that. The other thought that I wanted to leave you guys with before we dig in is the way that Sean Brett, this is a guy who does single file header libraries, things that are like pound include stb image, and now your code can just open PNG files without any extra libraries or anything like that. And what he did in one of his talks, Advice for Writing Small C Programs, was he pointed out that a lot of people try to memorize all of these functions and all of these things that you can do. But for him, it was much more intuitive to think about what the functions are doing. What are the steps involved? And that's something that really kind of stuck with me. So when he was talking about stir copy and all the different like random assortments of letters that are confusing and hard to remember, what he did is he broke it down into sort of like what is actually happening. So we're taking a source string, we're sending it into a dest, and we're moving to the next point. And one of the other major points that I think a lot of people have a hard time with is just acknowledging that null is 0. 0 is false. If you say if something, well, that's going to be true if it's not 0 and false if it's not. So just being able to think about that as the way that ultimately this is what's going to happen, and trying to get rid of some of the abstractions surrounding like null pointer and extra weird math with that, it makes what you're trying to tell the computer to do a lot clearer. So now that we're talking about stir copy, let's take a look at stir copy here. So what does the compiler actually output if I do that in my code? Oh, looks like the compiler is clever, and it actually just knows I want to just call stir copy, and this is doing something called tail calls, which mean that it doesn't even have to return back to this function. It just goes right back to where it needs to go. We'll talk more about that later. Okay, but what if I actually step through? Like, let's just show some assembly here, and we write it like Sean Brett. So we start with this up here, a load instruction. So we're taking a thing of memory, and we're storing it in a local value, and we'll talk more about that later. We can add, we can store back in another thing. That's what SB means. We can add, so we're incrementing along, and we can compare to see if we should stop running or not. And we're already kind of talking about assembly. Let's go a little bit further before we dig in with that. Strlen, also interesting. In x86, there's actually a single assembly language instruction you can use to do string length. But if you do strlen and you look at what the compiler is really doing, it's 7 more instructions. So you're thinking like, oh my gosh, why would it make all this extra code when there's an assembly instruction for it? And the answer is, on modern systems, my i7 I have at home, this is twice as fast, even though it's way more code. Totally unintuitive, but it's real. Like, you can actually profile these things. The big point of that is compilers are usually smarter than you. So don't automatically assume that you're going to hop into assembly and be able to make everything great and you're going to be able to outperform the compiler, because it's probably not true, certainly not at first, and maybe only a few times over a couple years, but you'll learn a lot and you'll be able to write better code surrounding it. So what is assembly? Assembly is instructions. Those instructions on telling the computer what to do map directly to the hardware. Normally, they have a very clear binary representation, so the assembly instructions just live in memory, and they can be executed as such. Usually, assembly is not executed in 1 clock per instruction. Not always true, but normally that's not the case. if you take a look at the back of your badge, there's actually a bunch of information surrounding like what the different instructions your badge can do, and all of those map to individual opcodes. Usually, assembly has registers. Registers are just like temporary values. A program counter, something to keep track of where the computer is currently executing the code. Basic operations like add, subtract, multiply, shift, compare, extend, like with sign. It gets a little bit hairy after a while, but don't worry about those. Those are going to be specific to whatever it is that you're doing, and usually the compiler can at least teach you some tricks there. Usually you can load and save from memory and maybe some I/O. Sometimes there's a hardware stack, and normally you have call, return. You might be able to have you usually have a conditional jump, which means like if some condition is true, go here. Otherwise, don't. Except with WebAssembly, which has this really, really long and vitriolic whole issue on GitHub. Let's just not talk about WebAssembly for a little bit. Okay. So let's break down a really simple example here. We want to write code that's going to call myproc. It's a function. It does something. I'm not really sure what. Probably print somewhere. And it's going to have a string, hello, and we're going to pass it the number 5. So you can't just like use a syntax where you're saying like, hey, I want to call this thing with these parameters. Instead, this is going to be extensa assembly. Sometimes it'll be stack. Sometimes it'll be something else. But the idea is what we're going to do is we're going to get the address in memory, which contains the word hello. We're going to take the number 5, and we're going to load those in registers. And depending on something called the ABI, what registers you use for which parameters and how you pass them in, that's always going to be different. But you can always look it up for whichever processor you're using. On the extensa, it's a little bit weird to make calls. You actually have to like load the pointer to the function. So it's like where in memory is the code for myproc. You load it into a register, and then you call this magic function, and it'll go handle calling the function for you. So you might be wondering, well, how do I have myproc? Like, what is that? That could actually be C++ code, or it could be C code, or it could be anything. And what happens is you take these source files. The compiler will then compile them to object code. Remember, code is just memory. And that all gets linked together so that when all of a sudden you're asking it like, hey, give me the address of myproc, now all of a sudden the compiler knows, or the linker knows, it's over there, and it can appropriately update the code. So assembly is the most basic mechanism for you to explain to the computer what it is that you want to do. It'll execute every instruction in order, one at a time. And I'm sure somebody here is going to say, well, actually, there are tons of exceptions to this, but we're not going to talk about them today. But let's go one step further to talking about what is a programming language. And so programming languages probably is, everybody here at least writes some sort of language, some sort of code sometime in their life. I think so, I would hope. If not, that's okay. I think you might be in the wrong talk, though. So we have two different types of major types of programming. One is called imperative or procedural, and one is called declarative or functional. And the imperative is much more like step-by-step, what do I want the computer to do? And declarative is more, this is how I would like the data to be at the end. Many times it's actually a mix. So the two are kind of declarative or functional, which is how should it be, how should the result be, or imperative, which is a more step-by-step how to do, how is the computer going to do it. Many times it'll be a mix, but most of the time during this talk we'll be leaning towards procedural just because it's easier to explain through. Yeah, and programming languages can be high level where like strings are first-class citizens where you can take two strings and add them. Just be aware that when you add two strings underneath the hood, it's still doing a lot of work. It's not a free lunch. Or low level where you're individually manipulating these things at a closer like layer. So top can be more C++, C#, that kind of stuff. Lower level is usually towards C. Or, you know, incomprehensibly low like raw x86 assembly, which even I can't read to this day. But some of you guys might be remembering, what about OOP, object-oriented programming? Well, object-oriented programming is bad, and there's lots of resources to helping you get out of that mentality. So what I'm hoping that you'll be able to get a little bit through here is that when you start working with assembly, it gives you a new way to think about the problems that you're solving. So you'll be thinking about what the computer is going to be doing, because you're going to want to tell it what to do. You're going to be able to think about those steps, and it's going to execute them. And you're going to be able to think more about the tools and the things that you have. How is the computer going to piece this together, and less about the paradigms or descriptions. And I really... Yeah, I guess like for my own life, I spend a lot of time kind of working in that push and pull between like the balance of paradigms, descriptions, tools, and writing things procedurally or more functionally. So digging in, we're going to get some tools. We're going to learn some assembly language, but I'm going to be teaching you guys the tools to learn an assembly language on the processor of your choice. And we're going to learn a bit about how to apply assembly reasonably. Most of the tools are going to work with most languages. So everything C, Python, Rust, all that stuff. Python's a little bit tricky because a lot of the tools will actually show you an intermediate thing, but that's still cool. It's still like, these tools are for all languages. Well, not all the tools, but some, you get it. Anyway, digging in, really what I'm going to be showing you much more is going to be how to include a little bit of assembly, a little bit of that salt with your C code, and how to just write C code better. So one thing you can see here, in this code below, it has an int16t. This is how it was originally written. This is some code for drawing sprites. And then the modification was we switch it to an int. You're like, well, what's the difference? It has to do less work if it's only 16 bits, right? And the answer is actually no. If you decompile this, you can see the compiler does a lot more work in order to use a 16-bit int than a 32-bit. In this case, this was for an ESP32S2. But yeah, no, goal, be like John Carmack, just sprinkle a little bit of assembly in. Let's take we have two more. I have two more things I'm going to dig into. One is I wrote this really simple function here on the right, which takes A, sets it to 0. Take A, R0. It's just we call A R0 because it's just going to be in register 0 for now. And we set it to the number 0. We're going to compare it to 4. So how does A compare to 4? If it's equal to, and you might be thinking, well, I said less than, but the compiler realizes that actually equal to is the most appropriate situation here, which is fine because it actually works out. So the compiler is not going to be a 1-to-1 for your code. But if it's equal to 4, then it jumps to the end. Otherwise, it adds 1 to A, and it loops back up there. So this is a pretty straightforward mapping of this function to this. The only problem is no compiler in their right mind is ever going to emit this code, because any kind of smart compiler is just going to emit this code because it knows the answer is 4. Like, this is how all the compilers, if you want to go through this, are going to represent it. But I thought it was useful for an illustration. One of the other examples I wanted to go through was the badge assembly example for the dice roller for this year's badge. I think there were actually some typos in it that I corrected, but I might be wrong, so don't copy from this slide in the comments. But the idea is that what we're going to do, we're going to just get the address at FF, which pulls a number from the random number generator. We're going to compare it to see how it compares to 7. If it is less than 7, then we're going to skip over this. And so say it's like 9. Okay, well, we're not going to skip over that. We got to go pull a new number. And then we're going to compare to 0. Well, if it's 0, we don't want to return that either because we want a number between 1 and 6. So then we're going to skip over 7 if it's good. But if not, we're going to go back up to the top and roll again, which is a little bit crazy. That I don't know who wrote that code, but I don't know if I would be the one to want to just keep rolling a 16-sided dice until it gets a number between 1 and 6. But I don't know, it works just fine. And then after that, we return from this function. And so now this function, getRoll, will nicely return a number from 1 to 6. So the core thing with the tools here, we're going to use Compiler Explorer. We're going to look at the output from OBJDump, which is a tool that comes with all the compiler tool chains. It comes with, whenever you're working with a microcontroller, you're going to have access to this. GCC with some of these extra really gross flags that'll give you an inline listing. GDB's Layout Assembly, also that's the same as if you're using Visual Studio and you switch to assembly mode. We're going to show a little bit about profiling, and we're going to look at a ISOdoc. So the biggest one, this is like the key thing that I hope that all of you get a chance to try, is godbolt.org. Matt Godbolt made this thing totally free, and what it does is it runs these compilers in the cloud, and you can go type in C code or Rust code or 44 languages worth of code in the left, and it's going to show you what the output is on the right. And this is so much fun to go in and play with this, be able to like go tweak something, see like, oh, actually, if I write it that way, the compiler totally misunderstands and it outputs like garbage code. And if I tweak how I'm telling the compiler what I want it to do, many times you can find that the code that you can make will be much faster and better. Also, this just happened last week where somebody was like, hey, what's going on with this code? It's using something called a Duff's device. This is a switch statement, and inside of the switch, it's not some cases, it's a for loop. And this is actually used in some situations for accelerated string copies, but like looking at this, I've been programming C for like 20 years. I did not know what was going on, but I put it into Compiler Explorer, or somebody on my Discord server put it into Compiler Explorer and pointed out exactly what was going on. So a lot of times, understanding this can help you understand how a compiler or the languages are actually working under the hood. The next one, the next big tool is objdump-s. There are other variants of this. I'll show you in a minute objdump-t. But the idea is if you have a binary file or an image which has debugging data, or even if it doesn't, what objdump-s will do, so it'll say objdump-s myproject.elf, whatever it is. This is an example where I looked at some code that was done on Espressif during initialization. In ESP32S2, I think. And what this does is it shows you the memory address where the code is going to be loaded. It shows you the bytes that represent that assembly code at that memory address, and it shows you the memory address. And it shows you all of this in line with the C code that outputted it. So you can see exactly where like, oh, so I have this for loop and it's doing these things, and it shows you right in line exactly what's going on with why the compiler is outputting the code that it is. The other kind of useful one that I think that people should be aware of is objdump-t. You can do the same thing, and what it'll do is it'll show you where in memory and how big all the different functions and buffers and all of that are, so that many times if you're like, wait, why is this function, like why am I running out of RAM? Why am I running out of space? Where is all this going? This will very quickly help you figure out exactly what's going on with why it's taking up so much room. The next tool is gcc-c-w-a-a-ad. It's a mouthful, probably won't remember it. That's cool. What this does, though, is this says you don't even have to go compile the code. Instead, I want you to show me while you're compiling it what you're thinking. And so the idea is here, while it's compiling it, you get a much better view of exactly like what the function calls are and what they're doing in the assembly code. Because it can kind of sort of rearrange it as it goes. This will give it a little bit clearer. It is really annoying to use for a variety of reasons. Mostly to do with it doesn't output to a file, it just outputs directly to standard out, which you can redirect, but it also doesn't fill in linked values. It's a little wacky, but if you're working on something small like an AVR or like a I don't even know, like one of the EFM8BB chips or an ST8L kind of thing, like this is going to be really useful for you to kind of figure out like, okay, my code needs to run fast, small, and good. This really helps you kind of understand what's going on. The last one that's of these tools is, I mentioned earlier, GDB Layout Assembly. This is the same as in Visual Studio if you go up to like View, whatever, Debug Assembly. And what this does is it'll let you see all of the assembly instructions that are being executed, and you can step through each assembly instruction. This is super useful in C++ because in C++ nobody can ever remember what the rules are with like virtual destructors and like what's initializing when, but you can step through it and you can figure out like, oh, actually I didn't mean to write it that way. That's going to be out of order, and sometimes it's going to double delete. Yeah. Point is, by stepping through in the assembly, many times you can gain an understanding as to what the normal code is actually doing. The last thing I wanted to touch on within this section was, well, actually there's one more after this, but was binary opcodes. And the idea is that, as I've said a couple times, Memory is code, code is memory. Binary opcodes are the things which are the actual like binary which represent the assembly. And so if you start thinking in those opcodes and you get used to them, it allows you to do some really interesting things. For one, at least when I was in high school, I thought that was the coolest thing ever, that I was not limited to BASIC on my calculator. I could write an assembly program and I could just spend days trying to get it to print hello. I don't know why. I thought that was the coolest thing ever. I did eventually get it to print hello. That's not the hello program, though. The idea, though, is that you get to be able to have this sort of superpower. Now, all of a sudden, you can start doing things like, you can all of a sudden start doing things with this code that would be unusual. So many times you might have like a router or something and you need to be able to insert code. So whenever a certain interrupt happens, you want it to actually go do something different. But you don't have that source code, that's proprietary or something. But you can go look up in like the interrupt vector and see what is it actually doing, where is it calling. You can make it go call your code first and then go call the other code. But it's really hard to do unless you're more comfortable with the binary opcodes. That's something that takes some time, but still being aware of what the opcodes are and how to use them is a really powerful tool. There's a lot of tools to help with this too. For instance, RISC-V, that's really hard to see, but RISC-V has this rvcodec.js where you can put in assembly codes or just raw binary values and it'll tell you what the assembly codes are. And so it's just kind of an interesting thing where if you start searching for it, there are lots of tools to sort of help with this. The last one in this section that I wanted to cover was isodocs. So just if you look up like extensa instruction set or AVR instruction set or RISC-V instruction set, what you'll usually find are these documents which will outline all of the different functions you have. And many times they'll even say how many clock cycles they take to execute. This is really useful if you're doing something where that like actually matters. Where you'd, instead of wanting to use hardware to synchronize something, you can actually just synchronize it using your code itself. So, talked a lot about assembly now. The one thing that is always being paired with this, though, is profiling, profiling, profiling. Because you might think you might be the cleverest person ever and it produced very little code, but until you profile it, until you see how long it actually takes, you really don't know. Like, I don't care how long you've been programming, you don't know. There's so many things all the way down to like the alignment of the instructions, like which byte they fall in, which will adjust the performance. So you really have to profile your code. And one of the nice things is, even though people don't seem to talk about this very much, there are some really powerful tools on microcontrollers to do that profiling. For instance, on Alt and Celica course, this is like ESP8266, ESP32s, everything but the C series, you can go use this function right here, which is a static inline function. And there's a special hardware register, which is the number of cycles the CPU has executed. That's it. So you can start, you can do something, and you can stop and see the difference and know exactly how long that thing took, down to the like 160 millionth of a second, or more actually, I guess, like down to the billionth of the second in some cases. If you're on an ARM, there's this magic register called cycle count, which if you just read that memory address right there, it tells you what cycle count your local processor is on. And in general, just always start, do something, and then subtract. Other kinds of optimization notes I just wanted to throw in here was that many times like processor or compilers will reorder instructions and you'll be left wondering why. Why is the code faster? But really there's a lot of unintuitive things that are very architecture specific. So a lot of times it helps to like profile what happens if I switch these two things. Does it go faster? And the answer is sometimes yes. For instance, I'm mostly familiar with Espressif right now, but like if you do a load and then you immediately use that value that you did, so you want to pull a number from RAM and you want to do something with it, it actually stops and waits for that to finish. But you could actually do other stuff in the in-between and then you can go use the value, and it actually is better for you to kind of like do some work here, do different work, now use this work. So just by reordering the flow of your program, things can go faster. I already mentioned instruction alignment, pipelines, which are kind of the thing I mentioned with the reordering. And compilers are usually smarter than you. So you are going to have to profile, profile, profile. So write code how you're comfortable, decompile it, write some hints to the compiler so like you can go figure out how to help the compiler understand what you're doing. If you can't make the compiler do the right thing, well, you can always just go write it in assembly. So let's just do that right now. The first one I wanted to touch on was inline assembly, and what this does is it lets you write inside of the language that you want inline assembly. Now the really cool thing is Clang, GCC, all the major compilers understand this to the point where this isn't a function anymore. What actually happens is the code will go compile it and be like, oh, they're calling this function. It will just replace this whole thing with the assembly code, and it'll refix up the registers to make it all match. This is great for integrating into other code bases, except when you get really complicated stuff like this. This is only, what, 4 instructions? But it's just totally inscrutable, the different like syntax that they use here. By the way, side note, I do have this talk and a lot of the notes around this talk on a GitHub project. It'll be at the end. Point is, this becomes totally inscrutable, confusing, and nobody can read it, which brings me to the next one, which is a separate assembly file. So remember how we have the whole thing where we compile and then we link? You can actually just code assembly code, and then this is now callable from all sorts of things. You could call the function from Python through a DLL. You could do it through Unity game engine, and it'll still just execute it because it's as long as you're using the right registers and knowing that like, oh, the first parameter is an A2 on this particular architecture, or the first like function parameter is an A2 on this particular architecture. Like that's going to be able to be called from and interact with all of your other code. The next part of this is linker scripts. You hopefully will never have to see these in the rest of your life. If you ever find out you need them, you should totally take like just Google it and look for examples. Linker scripts are the things that tell the compiler and linker where all of the different code should go. Where does your memory live? Where does your code live? Where does the interrupt vector live? Those sorts of things. It lets you do some really fun stuff with like being able to turn C into a scripting language where you'd be like, hey, I actually want to compile this to go live over here, and then while the program is running, you can like hot load different code in different places. It can just be a lot of fun to like make your development cycles go from like 30 seconds where you have to reflash the whole thing to I'm just going to go reload this little snippet of code and see what it does. So overall, please play this sane. Guard with defines, and what I mean by that is, if you're going to go write something in assembly, still have the C code there for when somebody else wants to just run it on some other processor. People will definitely want to run your code elsewhere. Assembly code is definitely harder to maintain, so just be aware of that. And optimize your code before trying to switch to assembly. But hopefully, being able to look at the assembly is going to help. So, at the very end here, I have some stories. The first one, this is one where like it really brought me to awareness, where red-black trees are like a dictionary, and C doesn't have a dictionary. So I was like, oh, I'll just use red-black trees, and guess what? Wikipedia has some example code that's written in C, so I'll just go copy and paste it. And they even have this note. They say, note that the inserting is actually in place since all the calls above use tail recursion. Remember how that thing where it just jumped to the other thing and magically resolved it? That's true. All of the functions here could use tail recursion, except that when you copy and paste this code, there was no compiler on the face of the planet that actually could optimize, on the face of the planet. No compiler I had available to me was capable of optimizing it. And so I had to go find red-black implementations that used it in a flat way. So instead of doing like recursion and stuff like that, it was just a much dumber loop. So as you can see here, in this case, this function calls itself, but the actual code is smart enough to know, oh, we can actually just like loop. It turns into a loop instead of being a bunch of function calls. But that's not always true. Sometimes compilers like TCC here have no idea what you're trying to tell it, and it just produces code that works, but is really slow. Another one that I wanted to touch on was when I used liquid nitrogen with an ESP32S2 to see how fast I could get it to go. Well, the flash dies pretty quick. It probably dies somewhere, I don't know, well above the temperature where liquid nitrogen keeps the chip. And the crystal also stops working. But by using a lot of these principles, what I could do is I could actually talk to the ESP over the UART while I'm also giving it a donor clock from another ESP. And I can go push code to it and cause it to execute. So I can go wake the chip up and do what I need to do without any access to flash or any of the other peripherals. and, well, okay, some of the peripherals, the UART to load it on. But then I can make an inner loop right here where I can turn, and one fun thing about the ESP32, S2, and S3 is they have Pro Alone GPIO, which is where there's no bus involved. It's only the innermost CPU core is now able to write to GPIOs, so I can look at the output. And the idea is I would turn on a pin, I would wait for cycles, and I would turn the pin back off, and I would loop. And that whole process takes 10 clock cycles. So I can measure what frequency the inner core is working with, which, by the way, ESP32S2s, I think they're supposed to only operate up to 160 or maybe 240 if you overclock them. I can't quite remember. But in air, they will kill themselves at, in this case, C70.71 megahertz. That's times 10 because it's executing 10 clock cycles of assembly for each one. So you can actually just overclock them up to 700 megahertz, or in liquid nitrogen, all the way up to 920 megahertz until, as you can see, some sort of catastrophic failure happens. So I needed the donor ESP, there's no flash, use the Pro Alone GPIO. I think that was everything. Oh, one other fun part was I did have to reverse engineer the PLL. And if I had tried to reverse engineer this using normal, like write my code, compile it, flash it, run it, that would have taken days. But what I did was I made it so that instead, when I write my code, it only hot loads a little bit of code. So my development cycles were actually more like, I don't know, like a quarter of a second between when I could run code and see the output, instead of having to go through the whole thing where you compile and run and all of that. Next one I wanted to mention was this thing called a BLED. The BLED was a little arcade light replacement, and it has its own, it is its own switch mode power supply. And the idea was using nothing more than an ATTiny13, it wakes up and it is able to self-program over the power rail just by turning the power on and off to it at the right times. It's fully like a PID loop controlled switch mode power supply system where it's using its own ADC to measure the voltage and be able to like control its power. And all of this has to happen in 512 bytes because there's another 512 bytes for the user to go write stuff in. So this was where I did a custom bootloader where I actually, code is memory, so I just went and put code in the middle of the bootloader where there were some unused instructions, so I didn't have to spend time jumping. You can just put code wherever you want to, and guess what? The computer is going to execute it quite like stupidly. So what I did was I kept profiling it, looking at the output of the crazy -WA-A-AD, and then trying to understand what the compiler was trying to do, trying to understand what I wanted it to do. And by then, at the end, I was able to actually get the entire program, all things, including like a CRC check, everything, all within that small thing. Another one was the ATTiny85 Ethernet. So this is an ATTiny85 running at a little over 20 megahertz that just has some has an Ethernet connection to some of its GPIO pins. And what I did was I wrote a little bit of assembly because I had to, but for the most part, what I did was I wrote the code very, very simply. So if you'll see each one of these, those C commands actually translate directly into an assembly instruction, and the compiler was able to understand what I wanted to do, and then the code is also portable. The second to last one here is the swagges. So there's this project that me and a bunch of friends from MagFest do every year where we make these like little remote control, not really remote control, handheld gaming systems. And in this case, this is the first year we have a full color LCD, which by the way, surprisingly cheap if you know where to get them, like sub $3. And we only had to add 15 lines of assembly, but overall we were able to increase the perf by more than 50% by working with the compiler and using the same tactics I've described. For instance, the only code we actually had to add was the multiply thing, because for some reason the compiler was too chicken to use mul16u. Some systems, yes, multiply is slow. Not on ESPs, multiply is really fast. So, and this is like, in my career, this happens like once every 5 years where I actually knew better than the assembler, so, or better than the compiler, but it does happen. And then another one I wanted to point out was oh, this was a clever one that I didn't see until I started playing with the compiler. If you have something where you're comparing total aside, but like I want to see if y is greater than or equal to 0 and y is less than 220 to make sure a pixel is inside of 2 bounds, there's actually an instruction, branch if greater than unsigned, which if you just put a little unsigned there, guess what? This code is now the same as that code, and it's one less assembly instruction. I just thought that was kind of fun. Very last thing here. So this is a RISC-V emulator written in a pixel shader running on VR chat. So you can just go visit this world in VR, and there's a pixel shader that is running on your GPU, and it's done by Pi. He's standing in front of it. He understood a lot of these principles, and like I mentioned before, like the opcodes, if you do opcodes and you really dig into it, being able to write like emulators becomes totally feasible. The inner loop of this emulator, I think, was less than like 140 lines long. It's like, it is surprising how much the familiarity with this can, like you start to see connections in ways where you can do a whole lot. One of the fun parts about this though is the main system memory is literally a texture on the GPU. So you can actually see it like booting Linux, decompressing like the kernel and everything else. So I just thought that was so cool. Yeah, so familiarity with assembly breeds empathy for the computer. And yeah, I wanted to leave with the last quote, which was on the written back of the badges. As far as I understand, it's actually by the person who designed the badge, if I haven't met them yet. But it's a programmer who has never coded in ones and zeros, is like a child who has never run barefoot on the grass. Thank you. As a note, I have to go run, so I can't really take any questions.